Perhaps let's get the what you would like out of the way. Are there questions about the semester test? The first announcement is that we did, you recall yesterday there was a request to have the test a little later. By convention, you usually have it begin in the middle of that session, or just near the end of it. So instead, we're going to have it begin at 1 o'clock. We're not going to have the usual, how to put it that way? Sorry. No, we're going to, I've entered it incorrectly here, but we're going to start at 2 o'clock. We're not going to have the usual tutorial. We will see each other at 2 on Discord. I'll make an announcement there when the semester test has been released. You'll have 2 hours to work on the test, and then there'll be an hour allowed, an additional hour allowed for you to compile and submit your solutions. All right. So that's just about the admin of it. And remember, you also have to include in your submission an honesty declaration. I don't see any questions in the chat yet. So, well, our markers, we mark our semester test and how the marking system work. Yes, markers will be assisting with the marking of the semester tests, but not like the practicals. They mark a few. The majority are marked by myself and Prof. Vandahar. And then there is moderation done by another academic. And then after that, you get your scripts back. So when you get your marks, as always, they won't be finalized until they have been moderated. Then they'll be finalized. So we'll have 3 hours in all? Yes, you'll have 3 hours in all. I'm confused with how you do when you use login. All right. Use, okay. We went doing primitive counting. All right. So the log function comes up pretty often because a lot of our algorithms, not a lot, but a significant amount of algorithms, make use of the divide and conquer strategy. That when you have a large problem, instead of trying to write a method that solves the entire problem, you break it into smaller problems, and there's all sorts of ways of how we can break up a problem, either by breaking up our input data, which breaks up the problem, breaking out what output we expect to get. There's also intermediate data and other things, but basically there's different ways we can break up our problem. And so because we have that process of splitting usually the input into half or some other portion, and then trying to solve the problem on those portions, which gives us an intermediate solution, which will then combine to get our final solution, we're often dividing the work over and over and over. And the log function simply happens to be the question, how many times can I divide a number by another number before I end up with something less than 1? That's all there is to it. So if it's log base 2, it's how many times can I divide n by 2? It's log base 2 of n. How many times can I divide n by 2 before I end up with something less than 1? And so if we're dividing our problem in half each time, the number of times that we can do that is equal to log base 2n. It also comes up in our trees because we're kind of having the opposite there. If it's a binary tree, we are doubling the number of nodes at each level. And so the way that it grows is with larger and larger logarithms. So we find it there as well. Can you give an example of code that has order log n? Yes, a very simple one is binary search. So you recall binary search, you start with can be an array, which contains sorted values. We want to find where in that array a particular value that we're looking for occurs, or if it occurs at all. We first start by checking the value at the middle of our array. So at the middle index of our array, we check. If the value that we're looking for is larger than that middle one, then we kind of get rid of the first half of the array and simply look at the second half. And we do that recursively until we end up with either nothing, which means it wasn't in there, or a single, or we get a hit, and one of those searches, one of those lookups in the middle of our array does give us what we want. What is the worst case? How many times can we do it? In the worst case, log n time. So that while loop that we have in that binary search, which you must have done several times by now, will be iterated in the worst case up to log base 2 n times. So it already comes up there. In primitive counting, do we need to show the total number of operations instead of 3n minus 1 for a loop? We just say for the loop is just n since we ignore constant. Yes, you do have to show. You are awarded marks for that. That's not to say that you wouldn't get some marks if you, by inspection, see that it is of a particular function type, which you can easily see depending on how many nested for loops you have, or if you have a while loop and you look at those conditions, you can tell straight away. However, the majority of marks won't be for that because the manual approach, whether you're giving pseudocode or valid Java code, is that we count those primitive operations. That gives us some expression that represents the number of primitive operations based on usually our input. And from there, we use our agreed upon method for getting rid of those lower order functions and constant multiples to end up with an big O notation. Why is it important to be able to count primitive functions? Well, there are a lot of functions that have the same growth rate in terms of runtime, but those low order functions and those constant multiples, whilst they don't change the growth rate of that runtime, they do change how quickly two functions the same growth rate run. Right? If one has constant multiply of 1,000, so it's 1,000 n operations, the other is n operations, not 1,000 will take longer. So although we distill it to a way that allows us to easily compare functions, we are also still interested in those number of primitive operations, especially if we happen to be working on the same hardware and software platform, and we're able to compare those algorithms, a lot more fairly than if we do it on different platforms, as we discussed. Okay. I've had quite a few students email and direct message me, and a couple came to consultation, and there were very specific questions, clearly about the past paper. Now, as I said, although you can guarantee you will be asked some of those questions, particularly the ones that are application questions, I'm sure one is going to ask, so yes, you will get something like a recursion trace. Yes, you will get something where you either have an iterative function or a recursive one, and you have to switch between the two. You will get one where you're going to count primitive operations, and you have to give the answer in big O notation. There's a lot more than just that. We've drawn questions from examples we looked at in class, practical assignments that you've been given. So please make sure you're not just studying the previous semester test or the exams that are available through the library. You should be looking at the notes, and wherever you have difficulty, wherever you don't understand something, then you actually have to go to the text to make sure you get a good understanding of that, and go over your practicals. All of that was to assist you in dealing with these concrete implementations of the abstract data types that we discuss. It's assumed that you now have that knowledge. So look over them. Where you had issues with anything that we've covered, make sure that you review that. And where you have time, if you completely finish studying your theory, spend a bit of time doing some coding so that you are up to scratch. All right, we now have another question. Which type of brackets does an array use as a parameter in a recursive function? Would it be public sum int square bracket array or public sum int square? Also was lazy. All right, so that it is the square one. However, the fonts that we used for, I think this is about the previous test, the fonts that we used for that is a really nice font. It's called Book Math or something, that looks really good when it comes to numbers and characters and all that. However, it does have this odd tendency of making square brackets look very, very similar to round brackets. All right, so I'm not using that font this time, which is unfortunate because it actually does look, it actually makes the text easier to read. All right, then what's a lazy iterator? All right, we had said that there are two types of iterators, and in fact, you can implement either type. Granted, we've only looked at the snapshot one. The snapshot one gives you an iterator over whatever data structure you have, whatever iterable data structure you call the iterator method on, returns you an iterator of the elements at that point in time. Whereas a lazy one will not actually extract, using extract very generally, but it won't actually extract all those elements so that you can use them in some whatever method you need that traversal for, let's say a for each loop. Instead, it simply begins at the beginning of this traversal we're going to make of the elements of this data structure. And then each time that you call has next or next, it then checks in the current data structure, is there something that appears after this? If so, and you call next, it then goes and retrieves that. So it doesn't extract all the elements. It follows whatever's going on in the data structure. And it only actually retrieves the next one when you call it. A lot of languages actually follow that approach. Certainly in Python, you can force that when it comes to lists and other data structures, because sometimes you're working with such large databases that it would significantly slow down your execution if you were to try and have everything in memory at the same time. The test will be more application-based than differentiating. Yes, well, certainly, because to differentiate a single linked list and a doubly linked list, you can just look that up. That's not to say that there's nothing in there that you can't look up, but we have attempted to make it where you have to use what's in the text and what you know, certainly what you know more importantly, to be able to answer those questions. And so you should, if you're up to date, not even need the text or the slides with you when you do this, ideally not. But you would not be unfairly advantaged if you were using that. And that's the point. So it is asking you to write some code, to analyze some code, to change some code, to fill in some classes that just have like skeleton code in there, like you've done in your pracs. And so it's drawing on all those things that you've learned thus far. Someone says, well, it seems like it'll be hard. It's a combination of those, right? It's some that you've never seen, and then of course some that, well, if you came to class and you went through the slides and everything, you should get enough to make it through. Right, but certainly if you are sorting for it, then it will be problematic. So some of the first lecture on the recordings disappeared with all this. Oh, no. By default, Blackboard Collaborate only shows you what it calls recent recordings. So just change the range of recordings that you're looking at. I will double check, but that's what it does. How many marks per chapter? It's not strictly per chapter. We've covered, what, 6 chapters? There are 5 questions. It is 20 marks per question, but those aren't necessarily in order. And it's not a specific amount of marks from a specific chapter. All right, I'll check that on Blackboard then. Example, AII. Is that one operation or 2 operations? Well, what did we say? Indexing into an array is a single operation. However, you understand that a 2D array is an array of arrays. So actually indexing into the outer array to reference a single array, and then you index into that as well. So it's 2 operations. We're doing runtime calculations. Must we mention code lines as we calculate? If you just give the number of operations in order that those lines of code appear in the given method, then it makes complete sense. right? If for some reason you're not doing that, that would be more difficult. Then you would have to give lines of code if you're going to jumble those up, but rather not. Just give them as they appear. If load shedding occurs, what's the procedure? Like with the practicals, we'll extend the upload time. So that even if you lose the entire 2 hours, you still will be able to have your 2 hours of writing time and upload time. To confirm, when we do recursion trace, we'll reach the base case and return the value. Do we place it inside a block? No, you don't place that inside the block. Just the convention we followed was those blocks actually method calls, whereas the values that are returned, we simply show with an arrow on the right side of that, and that follows back to the initial calling function, or whatever piece of code actually called that recursive function initially. Properties binary trees textbook doesn't explain too much on them. Yes, well, that's why I did explain them in class, because some of them, the text actually goes into quite a bit of detail, and others it simply does not. But the ones that you would not have to memorize are the ones I discussed, where, let's see, we understand that a list, if each node has only one child, degenerates into a tree. If each node has one child, degenerates into a list, and that list will give us the tree with the maximum height that we can get, because any other reordering, we take any child and put it as a second child to any internal node, will end up with lesser height. So that maximum height is simply starting at the first one, which has a height of 0 root, and then adding 1 each time we go down until the nth one will end up with a height of n minus 1. So something like that you should know and be able to discuss or replicate, because it's understanding that we want you to have about that data structure. The things where it's really just substituting your the relationship between external nodes and internal nodes, then kind of solving for one or the other, that doesn't really help. The one that I did explain, though, is a nice one, and at some point I will ask that on this test in one of the others or the exams, because that series of adding those binary numbers comes up a lot, and it's something that does not require you to go and memorize that. If you can add 1 to a number, just like you could add 1 to 999 and it gives you 1,000, you should be able to add a 1 to a full binary number, and you'll get that 1 to a higher power, but you have to subtract 1 because you had that. That is something that I particularly like to ask, because you have to explain what you're doing and then show you're working. Whereas for other things, you can just, okay, this is what's in the text, let me simply write that out. So even for ones where we're asking something similar to what you've had in the prac, or what's given in the text, we'll ask it differently. We'll ask you to use a doubly linked list instead of a singly linked list. We'll ask you to use a circular array instead of a singly linked list. We'll ask it differently so that we're testing, do you understand what we did there? Not just did you eventually get it right, and then just after that forget what it is that you did. So if we could show recursion in this way, is it right? 3 times product minus 1, then 3. Yes, but if we're giving marks for a figure, right, a diagram, and you choose not to draw that diagram, then you won't get the marks for that. There'll be marks for the answer, there'll be marks for the diagram. These are really giveaway marks. We're saying, look, this is something that is used, and you guys have done different types of traces, even from first year when you're looking at what values are stored in a variable. We have seen that it's a good part of the initial planning stage, design stages of our implementation or our software development lifecycle. And so we want to use those things. We want to learn what's used and be able to use those. To simply be able to, when you have a simple thing like that, like a factorial or whatever type of processing asked, doesn't give you any greater understanding or any additional tools that you can then use for more difficult problems. Right? The problems that we look at, because we have a single afternoon to do them, are usually simplified. But the tools that you're gaining from there, the skills and understanding you're gaining, you should then be able to go and apply to any complex problem. And ideally, from what you've learned last year, and the entire idea behind design patterns is that you are able to identify problems that are solved by specific types of design patterns. You're going to go there, and when you have difficult problems, try to break them up into types of problems that you've seen before, and then be able to solve those more easily. Now, granted, we're not rehashing those here, the design patterns, but we are gaining additional skills so that when you then see similar problems, you are able to solve them. And certainly that you're also able to discuss intelligently what's going on in the back end of these data structures, why it is that certain algorithms are preferable to others, because those are the kind of questions that are asked, certainly at job interviews, to see if you really understand what you've learned. And definitely not memorized any code to understand what's going on. Well, if possible, please show how you want us to show recursion, like to show the recursion trace. This we did in class, right? For some reason, my stylus seems to have absconded. All right, there it is. So you will recall, or if not, you should go and look at the recording. That when we discussed recursion, we said that if we have a function, let's take this product one. Okay, it looks more like factorial, looks more like that, because you're doing a product of some data structure like an array, then I expect to see that array there as well. So you have something, you have something like a factorial, and we realize that we can solve any factorial by initializing some product to 1, let's say prod 1, then going through a while loop, each time multiplying by n, then n minus 1, then n minus 2, then n minus 3, until we get to, let's say we are decreasing some temporary variable that's initially stored, set to n, or just n itself since it is passed by value, likely if it's a intrinsic. Then we can just decrease that until we get to 1 and we stop there. So we could do this with a while loop. Right? We could certainly do that. But instead we say it would be more elegant to create a recursive function where we say that for any factorial, you can work that out by either if n is equal to 1, then simply returning 1. Otherwise, so here we have that n is some larger positive number because factorials aren't defining those negative numbers. Then you can work it out by finding out whatever fact n minus 1 is and multiplying that by n. So we're working from positive integers, we're decreasing them each time by 1. We should work towards 1. All right, some text will use 0 as the last valid input, and they'll simply set that to 1 as well, the factorial of that. So it really doesn't matter. You're simply multiplying that factorial by 1 in the end. Regardless, we would like to see, well, what's actually going on when I call this recursive function with a particular argument. And we've agreed that we can draw a figure called a recursion trace that will represent that series of calls. So let's say I called fact 4, right? So I called this recursive factorial function with an argument of 4. It won't return anything because 4 does not fall into our base case. Instead, it will do a recursive call to the same function with an argument that's moving towards our base case. If it wasn't, then we end up with an infinite number of these calls that would get us nowhere. Then fact2 and fact2 calls fact1. Now this can actually return something. What do we get? Well, it falls into our base case. So we actually get this value of 1 that's returned. That is actually done something with by that calling function, would have been fact2. It then returns that value to fact3, which takes whatever that was and multiplies it by n, and returns that to fact4, which takes whatever that was and multiplies it by its n, which is 4. And that's the final answer. Okay, we usually say something like that's final answer, or that's what's returned to the calling function. Both of those are allowable. So this shows what the series of calls for this particular argument look like. So it helps us to understand what's going on. And certainly if we see that in our design phase, oh, we're not moving towards our base case, that's a problem. Or you'll recall that when we discussed in chapter, was it 1 or 2, we were talking about Java and testing and all that, we did discuss the fact that you should test your methods with a representative set of inputs. You should check those extreme cases, the special cases. You should add for debugging things like print statements or whatever else, use your IDE. So we should actually be doing these things before we even implement it. And when we implement it, then check it with even more things. Because we can certainly programmatically create sample inputs and then test it with a whole bunch of those. So this is really a precursor to that. We want to see, is our logic correct? If it is, then we start implementing. Otherwise, we're wasting our time. Right? Our 40-20-40 rule says spend 40% of the time on design, then that 20 on implementation, then that 40 on testing. And what I've seen is that I don't know if you all are spending the time on design, but certainly there's a significant amount of time that gets spent on testing. We're doing this in the labs, and that is what you should be doing. You wouldn't implement all your methods. You implement a method, you test it to make sure it works correctly. Right, remember we had some strategies for that. Then we keep going. All right. Why did the fact end at 2? It didn't end at 2, ... There was a fact 2 there, it ends at 1. Okay, it may not be the prettiest one, but that is a 1. Then 1 is returned. That is then used for the next one, and so on. All right. I think I've already mentioned the majority of the things that you can expect to find there, but what I want to note from what I saw from the questions that I got was that perhaps you're expecting it to be the exact same as the ones the previous year. They won't be, and they won't be exact same as what you've done in the pracs, but if you've done those, you should be able to do these. And certainly the more difficult things are awarded more marks. You should follow the strategies you always do when you're writing a test. You have to write each question or answer each question in its entirety, but you can choose where to start to build up your momentum. But even in the order that we ask them, it kind of follows that rule, that we ask things that you should know, should be comfortable with, and then kind of build on those. All right, that's actually almost most of our time. So let's spend a little time introducing the next topic. I'm not going to go into it deeply. I really want to introduce it. I'm sure we will have to repeat most of this next week, but it certainly helps that when we start applying it and using it in the next prac, you will be able to feel comfortable with it. And that comes from being exposed to it over and over. What was the formal definition of depth B? We said that it's the number of ancestors of a node, not including that node. So what you've given there is the recursive formula for finding it, but not the definition, but you could give a recursive definition. All right, so we want to talk about a priority queue. It's actually different from the other LETs that we've been dealing with thus far, because for all our LETs, we've stored an entry, an element rather, not an entry, an element of some sort. Yes, we've used our generics framework to show that we really don't care what type of element that is, but any object can be stored there, and we do things with them in the order that we've discussed in our different lists. However, here we're going to store not just an element, but a key that has some meaning. And this is true for the next few ADTs we'll discuss. But for priority queue, that key implies some priority over those elements, and allows us to determine which has the highest priority and to extract and do things with the entry that has the highest priority. When I say entry, I'm referring to both the element that's stored there, the object of whatever type, and its associated key. All right. Where would this come up? We'll actually look at some example of that, but it comes up in life that when you are deciding what task to do next, you will decide that based on the priority of tasks. And it may not be as simple as the order in which they came to you. Oftentimes it isn't. It is some combination of factors that you, without even knowing, compile in your head and use that to generate a key for each of those tasks, and that decides the order in which you do them. So it does come up even though you may not think of it explicitly. So it's an ADT for storing prioritized elements. So we don't have that same idea of simply an order that's dictated, for example, in a stack or a queue by the order in which things arrived. But here, rather, they can be inserted in any way. They don't have to be inserted into our priority queue in a specific order. But when we remove elements from this, we have to do it in order of priority. Different texts use different things. Some will assume that the lowest priority, or rather the minimum priority, is the highest priorities. Others that the maximum priority is the highest priority. We assume the minimum route, but you will see that certainly if you look this up online, there are different, the different texts use different conventions. So if we want to remove the thing with the highest priority, we'll actually be removing the minimum, the entry with the smallest key there. Right, so that's what we are trying to do. And this key is used to identify this element. It should have some meaning associated with that element because it's usually derived from some attributes of the element. Then we can store it within a priority queue and use that to remove things in order. Right. The key is not necessarily unique, and they can be of any type. So these entries now are not single elements. They are a pair, a key value pair. That value can be, again, any object. We also have this key that's associated with it, and we use that key to be able to retrieve entries in order. Now, the point that's given here is that priority queues store entries to allow for efficient insertion removal based on the keys. We will see as we look at different ways of implementing our priority queue that we can either have efficient insertion or efficient removal. It takes a bit more work to find that balance to get efficient insertion and removal, but we do get there. Right, so this is the first really big new idea, although we have been using without quite realizing that to be able to put things in order, we must be able to compare them. You must be able to say, given two keys, is one key greater than the other, or is it less than the other, or is it equal to the other? And we already said that we allow keys to be of any type. And so the one caveat is that they have to be able to be compared. We have to actually be able to define an order on these keys to be able to find a min or a max. You'll recall from your first semester first year that your algorithm for finding a minimum is you assume some very small thing or some very large thing or some initial thing in the collection. Then you scan through the collection, each time comparing my current minimum is what I'm looking at less than that, and I'll update my minimum if it is. We have to be able to compare these things. Thus far, we have used things that already, that kind of have a built-in method of comparing. And so when we call these operators, they just work. But now we can define our own relations to be able to dictate how two keys should be compared. All right, why do I say that we've already been discussing this? When we've been saying that a queue or a deck or a stack has a linear order on its elements, on its entries, on its elements, though that actually means that I can put them into an order from the smallest to the largest. Right? Granted, though, in most of those, it's simply the order in which they arrived. But to be able to say I can, going from that idea of a set and then adding the idea of order to get that concept of a list that we began with, we were already kind of implying or assuming that there was a way to compare and thus create a total order on those elements. And now we realize we actually need certain properties to be able to have that. We're not just given it. All right, so because these keys can be anything, we need to have some way to be able to compare them. And what we need there is called a total order relation. So the notation that's given here is not the same thing as less than or equal to, right? It's a stand-in for some operation that will allow me to compare two things. And it should meet these conditions. The properties should be reflexive, as in a key should be less than or equal to itself. So let's look at a relation that you have in real life, the relation of being a sibling. You may be able to argue whether or not, but I would argue that you are your own sibling, right? Siblings are people who share the same parents. You have the same parents as yourself. You are your own sibling. Asymmetry, which says that if x is less than or equal to y and y is also less than or equal to x, then x and y have to be equal. That you can't have that one is both less than and greater than the other. All right, so if we're talking about the order in which siblings are born, you can't be the eldest and the youngest. Rather, you can't, certainly if it's only you can, but you can't be older than and younger than another sibling. And then transitive, if one is less than or equal, if x is less than or equal to y, and y is also less than or equal to z, then x is less than or equal to z. So if you have a sibling and that sibling has a sibling, then you are also the sibling of that third sibling. Right. So we need to be able to define such a relation to be able to compare the keys, and we need to be able to compare the keys because we need to be able to order them to know which one's the smallest to be able to retrieve that entry with our highest priority. So again, it stores this collection of key value pairs. The methods, the main methods that will be for our priority queue will then be insert kx that inserts a key value pair. So a particular value with a particular key, and remove min, which removes and returns the element with the smallest key. So that'll really be the only way that we access things from our priority queue. We will retrieve that min, retrieve the min, retrieve the min each time to decide, well, who should be next in line? And we have some applications that we're given here that this could be used for standby flyers or for an auction or for a stock market. Let's think about those standby flyers. So you have people who have booked seats on a plane, or instead they've actually bought tickets to be on a particular flight. But you know that most airlines routinely overbook flights because a certain percentage of people will not make it. A certain percentage of would-be passengers will not make it to a flight. And so they book a certain number more than that. What happens when everybody comes, or more than the number of available seats? You have more than that number of passengers who are there at the airport. Well, then you put them into a waiting list, right? And how do we decide how those people should be called from that waiting list as spaces appear? it's not a straightforward thing. It's not just, well, you got here first. It's usually some combination of, well, what type of ticket are you booked on? So what class of ticket? Is it first class, economy, business? Yes, when did you book? Are you part of the frequent flyer program? So there's a variety of things that are used to compare to passengers, but we have to be able to compare those two passengers to say which of them has the higher priority. If we can do that, then we can always say, okay, from this collection of people who are waiting to get onto this flight, we know who should be given the next available seat. It's the one with the highest priority. All right. Auctions as well. If we're talking about your English auctions, then yes, you would simply look at price, but you'll recall, or you may not recall from Informatics 2B, that we have other types of auctions like Dutch auctions and Yankee auctions, where instead of simply considering who has the highest bid, with the Yankee ones, you also consider what quantity they want to purchase. And certainly when it comes to the stock market, you're trying to, for each sale, you're trying to match that sale up to the best purchase bid. And that is not just who's willing to pay the highest price, because if someone wants to buy one stock and another wants to buy 1,000, then you'd be more interested in the 1,000, even if their price is slightly less. So it's some combination of what price and what quantity to decide which has the highest priority of all the purchase bids. And that will be satisfied first. You remember in our prac, we took a very simple approach. We said that when we have all these buys and then these sells, we satisfy those cells simply in order that they are requested, and we keep, or rather we want to get rid of the stock that we purchased first. Right, but in real life, it's a little more complicated than that. Right, there's a comment here. Would NoSQL database use a priority queue as it stores data in key value pairs? I really wouldn't know. All right, I haven't worked with NoSQL databases, so that is an interesting question. If you have the answer for it, then do bring it. We can discuss that. All right, I'm actually going to stop there. We are going to go into another ADT that we use to do the comparison. All right, but the inner workings of that we can look at next week, because I don't want you to simply forget all we discussed. You should still remember next week that this new type of ADT doesn't just store your regular elements and have that single method that can retrieve an element. Instead, now we store key value pairs. Those keys should have some meaning, some relation to those values that we are storing, and they allow us to be able to compare those entries based on those keys, and we're able to then get whichever entry has the highest priority by finding the one that has the minimum key. To do that, we must be able to compare the keys. All right, so we'll leave it there. For those who arrived a little later, please note that the test begins at 2 p.m. tomorrow. It'll be released on Eve. The notice will be posted on Discord. You'll then have 2 hours to work on it, an hour after that to submit. Right, so if there aren't any other questions, we'll stop there. There are some comments. Yes, we agreed that the markers will be changed after the semester test so that we don't have the issue of overlap, or rather the issue where someone marked your test but you can't query, or someone marked your prac but you can't query because we've switched those. All right, so I would suggest that you direct message your markers if you need to during this week from the deadline today, which was at 12, to the next week. They can respond, and by the time you get to the next prac, when they have switched, they have satisfied whatever queries you had. We're asked about dictionary. Is it similar to the dictionary? Yes, we'll get to that. It does work in a similar way. You again have key value pairs. Again, it's also similar to a map, except that dictionaries like these don't have to be unique. And dictionaries, it's more you're concerned about being able to retrieve things efficiently. Here, it's well, you only have one type of retrieval, that retrieve min. So as long as we have an efficient implementation for that and inserting into our priority queue, then we can get a good one. Would a tree be a priority queue? Thus far, we haven't really looked at what concrete data structures we could use to store this queue, but we will see that we can store it in an array, as always, and in a tree, and it works rather nicely with that tree. Right. What's the next pack on? It hasn't been set. I think we are due to do trees. So I'll make one with trees. I will stop the recording there. Thank you very much.